I think we should start, right? Hey everybody, welcome to Percona Live. Yeah, it's nice being here again. And today we're gonna talk about Postgres. So this is our agenda today. So basically, we're gonna have a little bit of introduction on how Postgres stores data. It's important to understand how Postgres stores data. We're gonna see a bit of the internals, how the data is organized. So then we talk about indexes. What are indexes? So as I mentioned, they are basically data structures, right? Not really too much there. And we're going to talk about something that's very important in Postgres that we really understand well. And about table and data access. How the data is accessed by the database. And disregard if it's access to an index or directly. And we will understand why many times you create a nice index in your table. You do a select and the database just ignores that index. So it was not there and go for a full table scan. Right? So it usually happens a lot on the database, and we'll understand why Postgres sometimes likes better to do a full table scan than use the indexes. We're then going to talk about the join operations, how the joins are made on Postgres. We have a few types of join in Postgres. We have the good old nested join, the nested loops. So this is our favorite one right here. We do explain and so nested loop. That's awesome. We're going to see the hash joins, the merge, and the parallel joins, how they works. And another very important thing that we need to understand on database on Postgres are the operators and the data types.
Initially, it was not there yet.
That we will explain a lot as well on how things run inside of the database.
High availability and Charly.
We're going to talk about a few database indexes. The good old B3, so is the most common, is the default index. When you use Postgres, every time that you go there and create a database, you're going to get a B3 index. So it's good enough for the majority of the situations, but sometimes good enough is not just good enough. Sometimes we need something better, right? Something that is more specialized. For example, an inverted index or a block BRIN index. This is something that we do not see often in other databases. And it's also highly misunderstood how that works on Postgres. Sometimes people get really mad about those type of indexes because they're expecting something they do not happen. So after talking about those indexes types, we're going to do some work. Let's work with indexes. Okay, how do we find the right or better index type? How can we use multiple columns or partial index on the database? So can we use functions or can you use expressions to define an index on Postgres? We'll see that's also quite interesting and can improve a lot of performance. We're going to also see how can we drop and create index safely on production, because that's a problem on Postgres. Every time that you just do it, create index on the database, on Postgres, that's going to put some logs on your table. And those logs are exclusive logs. So exclusive logs and production, they usually do not go well together. Right? So those are some things that we usually do not want to see. And by the end, we're going to have a conclusion. So this is what we're going to talk today. And let's start on how Postgres stores data. How is the data stored on Postgres? Well, Postgres use one data structure that they call HEAP file. Different from other databases, this data structure is quite simple. It has nothing fancy there. The data is just organized and put one after another. So the files are separated in blocks. As we're going to see here. So we have blocks on the HEAP files, and every time that you do an insert on the database, you just write something here on the first available position that you hold that release. The blocks on Postgres, they are of 8 kilobyte size. So the default is 8 kilobyte size. We cannot change the block size by configuration. If you want to change the block size, we need to
memory
recompile the
storage
data.
that's not available anymore.
So there is a parameter of the compilation time that we can change the database. So there are some circumstances and some situations that's interesting to change, but they're really specific situations. Most of the time, I mean, 99% probably of the time, the 8 kilobytes block will work for this purpose. And one thing that we need to understand when working with the blocks and the database is every time that we do a select and every time that the database is going to get one data, it gets the whole block. Doesn't matter if I do select ID from stable user where ID number 5.
Compatible in the protocol level.
It's 4 bytes, right? ID integer 4 bytes. So it will get 8 kilobytes into the memory.
For the MongoDB.
This limitation comes first from the CPU because the CPU always get from data files the block size that they are most of the ones today. They work with 4 kilobytes block size. So the database they also work
there are also some graphical tools as well.
And as you can imagine, one block of 8 kilobytes can store a lot of data. Right?
And Atlas has which you can use to.
And one problem that we have on the majority of the databases is when we start doing some things that we call here now. No, I don't have here. Random I/O. For example, when we work with MySQL use a different storage type. MySQL use cluster indexes. So when you create a table and you create a primary key, the table is physically organized by the primary keys.
Okay.
So inside of the file, we have a B-tree.
One or more databases. So
it's really good when we are doing a select that we have a specific index because it's a B-tree, which goes to the index and we get all the data that we have. It's highly efficient. But it's very inefficient when you need to traverse the whole file. The heap file, for the other hand,
the MongoDB instance
they just put one block after another. So there's no organization inside of this file. You're inserting, you're just inserting one after another. So we basically have a sequential file.
And it will operate with
it's a lot faster and cheaper for the database to traverse the whole data file, the whole heap file, than use an index, for example.
Or any of the ones that we just saw.
Because sequential I/O is a lot faster than random I/O. Right? And that's one of the reasons why Postgres prefers to use a full table scan than to use an index. When we create an index,
if you're already connected to the instances and you don't see any process yet, it will be our job to install it. Okay. For those of you that are right, after, I'll explain how to connect.
We do have some, but they're not really efficient. Like Postgres, it relies a lot on the OS, on the kernel. Postgres doesn't do direct I/O, for example. Right, like MySQL that does direct I/O, so you have everything, so you can work on the database. Postgres doesn't do that.
The files for each of the collections plus.
And it uses the OS cache.
Depending on how you.
So most of there are some optimizations, there are some parameters that you can tell the database that the hardware they are using has better I/O. Like for example, is an SSD. So it will favor more to use an index in that case. But still, the index is going to be more expensive because even on SSD, random I/O is still lower.
The collections is similar to a table.
It's not like you're talking about spinning disk, like there was order of magnitudes, but still like 3-4 times most of the SSDs. So, but yeah, answer your question on the database because it relies on the kernel. And that's interesting to know as well because when we do a commit, whatever transaction you do on the database, so the database will ask the kernel, ask the OS to save that file.
Another thing that's different is that
so it's up to the kernel to save or not the information.
MongoDB will
so the kernel might just instantly save or put on the kernel cache, that usually probably happens, on the file system cache, and then at some point that will be saved. The few operations that the database traverse are when we do a checkpoint. So the checkpoint, it will really run fsync on the cache, on the OS cache, and they'll force the cache to be flushed to the database. Why I'm saying that? I'm saying that because when you go to the internet, there are some optimization. Search on Google, optimization IO for Postgres. Postgres has a parameter that names fsync that can be enabled or disabled. A lot of blog posts on the internet, they tell you to disable the fsync because you're optimizing your database IO. Yeah, that's true. If you don't like your data, that's highly efficient. Really highly efficient. Yeah, that's going to be faster. It will be fast because, well, you have no guarantee anymore if the data is going to be saved at the disk, right? So don't trust and believe everything that you see on the internet, especially about database. There are a lot of misleading information. So back here, the pages, they are really close to each other. So what the database does, it tries to allocate some space on disk, and it always put one block after another, literally like we see here. And one thing that we need also understand is Postgres doesn't split the data into multiple blocks. For example, MySQL it does, right? So if you have a really large data, you can have that data split in multiple blocks. Postgres doesn't. And then you ask me, how can I save data that's larger than 8 kilobytes, for example, a JSON? The JSON also is stored inside of those blocks. Postgres has a technique they call toast. We talk about later about those techniques. But every time that we have data that's larger than 8 kilobytes, or half of the block size, that's the limit for the data, is half of the block size, it will be stored somewhere else. And that also makes the access a bit slower, right? So keep that in mind when you design your database. So yeah, we have the heap files. The blocks here at 8 kilobytes, they've been stored at. As I mentioned, it can only be changed at the compilation time. There's no parameter on Postgres to change the block size. And be careful when you change the block size because your database is going to be incompatible with the default configuration. It means you cannot use streaming replication, for example. Because the Postgres streaming replication is physical replication. It replicates blocks of bytes. It's not logical replication. It does not really only replicate the data. So because the blocks are at different size, now you are stuck with that block size. And there's no easy way to get around of that. The safer way is to do a database dump, a logical dump, a copy of the database, and then load somewhere else. That might be a problem when we have, for example, a few terabytes of data. So we have a customer today, they are having this problem. So they changed it a few years ago, the block size. Back that time made a lot of sense for the problem that we're solving. But today, things changed. And they want to go back to the full block size because they have a huge part of the databases, and this very only application is stuck and they cannot replicate. And the problem is they now have 1.9 terabytes data and they cannot afford a long time off. Yeah.
Big file has a limit of 1 gigabyte, but with access you can further.
Very good question. Very good question. Yeah, the heap file, it has a limit of 1 gigabyte. What happens is when your data, your table gets more than 1 gigabyte, you just create another file and link internally one file to another. So for the application, for the operator, for who is using the database, you have just a single file. But inside of the database there, you're going to have a lot of files of 1 gigabyte that refer for the same table.
Yeah, so when you query, it will be faster because multiple.
Not necessarily. Not necessarily. So it does help, but also creates other problems. Like everything has a good way to see and a drawback, right? So the thing is, when you're accessing a file, it doesn't really matter how large the file if you are accessing at a certain point, if you have an offset. For example, you do a select and you have an index, and that index has know exactly the location of the information you have. So just tell the kernel file, I want to look at this file to this offset. So you go on this, exactly that offset, and get that information. It doesn't matter if you have 1 terabyte or if you have 20 terabytes of the file size, right? The problem happens when you need to traverse that file. So if you have a single file and you need to traverse the whole table, it's a bit harder for you to, for example, do parallelization. You need to have be a bit more smart to split the file internally to do parallelization. In that case, just because you have many different files of 1 gigabyte, you can easily parallelize the full table scan, for example. Each thread, each CPU core can get 1 file, get information, put back in memory, then you just start sending it to the client that is reading the application. That's one of the benefits. But to just access the data inside of the file doesn't make really much of a difference if you do. Right? So, yeah. As we see here, the block files are the full 8 kilobytes, right? So, in a table, all pages, they are logically equally, they are the same. So, just because it's not organized like as an index, it's just normal file, all pages are basically the same. They have a header. On the beginning here, they have a header. And then we see what they call item points. And it's kind of funny how it's organized inside of the database physically, because we don't have data here on the beginning of the block. The data, it grows from the end of the block towards the middle. And we have those pointers here. They literally point to the data. If you do a select, and let's say you have an index, and the index will tell you, okay, I need information on the block number 8 on the position number 17. It will come to the block. The position 17 here going to be one of those pointers. And then the pointer will really tell you where the data is stored. Weird, right? Why don't we just have the data here? This approach, it helps with one optimization that Postgres has, they call HOT, that heap only tuple. So what happens when we do an update on the database? What do they do? Postgres doesn't change the data on the spot. If we have the data here, let's say we do an update on the tuple here, Postgres will copy this tuple and save somewhere else. Remember, when we have an index, the index needs to be updated to have the new address of that information, right? Because if you do another select, I don't want to get the old data. So the index needs to be updated. If there is a space here inside of the same block, the only thing that changes is the pointer. Now instead of update the index, the pointer just points to the new location. So if we can keep a space internally here in the blocks, and this is when one parameter that fill factor comes in handy, you tell how much space or how much more you want to fill inside of each block. We can leverage performance, especially for updates, having the hot tuple only.
So just so I understand, you're saying that the index only to the page header and the final within the page header.
Yeah, the index point to the item that does, yeah. It's not the page header. The page header has more information about the page itself. So it has information what are the types of the data that we have there, where it ends and it starts. So it doesn't have information actually about the tuples. These guys store the position of the tuples. We'll see later here a few examples that we can inspect that on Postgres. There's an extension on Postgres that we can inspect and check what we have inside of those files. That's pretty cool. And yeah, they point here for the data actually. And the index has an address of those individuals here. The index doesn't have the address of the tuple itself. Well, let's say we don't have space here anymore, right? So that's when you move to another page. So when you move to another page, that case you need to update the index. Exactly. Yeah, we update here and then we update the, yeah. Exactly. Yeah, because you need to tell this guy here that this page is not visible anymore. It's a dead page. Not a dead page, a dead tuple. So it's a dead tuple, and then it will point to another location. Exactly, yeah. Yeah, there is a problem in Postgres about that is write amplification, right? So it does cause write amplification, especially depending on the design that we do. And it can get a lot of worse. I'm gonna have a talk day after tomorrow on how to save money using data modeling. That's basically going to talk about data amplification and really how it's organized internally. We're going to run some examples, and we'll see that we can save up to 30% of disk space just changing the location, the position of the columns inside of the table. Yeah, and answering your question, Marco, yeah, it does. It counts like if it definitely has the right amplification because you need to write in multiple places, but if we are not careful enough, it can be a lot worse, right? That's indeed a problem. So, yeah, this is how the row is organized. So the row also, they have their own header. When we access the database, we have the header of the page, right? So the header of the page gonna host some special data here for the access methods. We're gonna see what are those access methods. So they're gonna hold how much space is being left, how much we can allocate. So those are information from the page itself. When we access the data, the tuple, then we also had a row fixed header. So on the whole header here, we have now information about the tuple, the data itself. For example, it will tell us if we have nulls or not. And this is interesting how Postgres implements nulls inside because it's just a bitmap, right? So for example, if we have 10 columns here, that we're gonna have 10 bits literally here, where one indicates on that position, the column that position is null, 0 saying that the column that position holds data. So a null inside of Postgres, it just allocates literally 1 bit of information. It's really cheap for the database work with null. And there's also information about where the page stops and it starts. Because if we go back here, basically the item, the pointer, is pointing to the beginning of the page. So that inside also has the address on how many bytes we have up to the end of the page, so the database doesn't cross the boundaries of each data. And see how complicated it gets when we change the block size. Because a lot of those information, they're really dependent on the block size the database is using. So that's why it can be really problematic when we do change the block size, right? So this is a better picture from that one. And this is a really bad guy, padding. Do you know what is padding? Empty space, yeah, but why do we hold empty spaces here? Alignment, that's the secret word. CPUs, they are picky. They like to work with the data that are aligned, what they call the word size. It depends on the CPU. If you have a 64-bit CPU, the word size is going to be probably 64 bits if the vendor is not weird enough to make something, right? So, and if ever the data that we have here is aligned with that CPU word size, it means CPU are going to work smoother, so it doesn't need to do more cycles to do the same job. If you lose alignment to get the same information here, let's say it's misaligned here, to get the same 64 bits of information, CPU will need 2 cycles to put in cache. So it's very inefficient. And what Postgres and most of the database, if not all of them, they do, is they always work with aligned blocks, aligned data. And just a preview from the talk, what does that mean? Let's say we have, let's do an exercise. I'm gonna just create a table here. Pretty simple one, nothing fancy. I hope I don't have a table with this name already. So I'm gonna put here vaca whatever size, and ID gonna be integer, and I'm gonna put age, they're gonna be a short integer, and address, that's gonna be another vaca, 100, right? So the problem here that every data type, they have its own size. So an integer in Postgres is of 32 bits, 4 bytes. A short is at 2 bytes. A varchar is undefined. So when I create this database and I start storing data here, remember the data needs to be aligned. Postgres aligns data with 8 bytes. That's a long integer, right? So the problem is this data here is not aligned. And the next one has 4 bytes. So probably we need some padding here to make it to fill up to the 8 bytes that I need. Alignment. It's because of the word size. In this case here, we're using a 64-bit CPU. 8 bytes, right? So because of the word size here, we are using 8 bytes. So it's going to be aligned that. So if we start a column that's smaller than 8 bytes, and the next column just complete the 8 bytes, there's no problem. Like for example, 2 integers, one next to each other. That's perfectly fine. Right? You can fetch them together within 8 bytes. But if you don't get the boundaries correctly, then we have padding. And padding is bad. It's bad for performance and also bad for space. And that's why, like in a really simple exercise we're going to do, we'll see that we can get like 25–30% space disk difference. If we have 1 terabyte data, that can be quite something, right? So the toast, the thing that I was saying, remember, Postgres uses a fixed page size. The full is 8 kilobytes. So, but what happens if our data cannot be stored in 8 kilobytes? Postgres has what they call the oversized attribute storage technique. Nice name, right? Like, in short, toast. What it does, it creates a new file and store the data there. So every time that we create a table, and on that table that we have defined a column that is too large to be stored on the page size, the database will automatically create a toast file for that table. And those information will be stored there. So when we have a text, when we have a large JSON, or all those large individuals, they'll be stored here on the toast. Right? And we need to keep them in mind, especially when we are doing a select. Let's say we do have a table, user table, and we store the user picture, the photo, on the table. And the application only needs to the login ID and password to do the login, right? Doesn't need any information else. If the application does a select star, it's asking all the data from the database. What happens? Postgres will access this toast. If we have hundreds of gigabytes inside of the toast, we access the toast for nothing. And that's gone from disk to memory, from memory to the network, all for nothing. See, when we tell the developers, do not use select, or do not select all the information, for some database it's fine, but for Postgres, when we have large columns there that's been toasted, it's even worse. Because we are making your database working a lot more for nothing. So when designing the database and working with the application, with the developers, always try to make sure they only get the information the application needs. That's a very basic optimization, because we don't need to do anything on the database. We don't need to change any parameter or anything, right? It's pretty simple and straightforward. So how does it work? Well, when the role is too large, it's larger than 2 kilobytes by default, the toast mechanism will create the file and will be attached or linked to that page. So every time that you write something and needs to be toasted, it goes there. The toast is also stored in blocks, but the blocks, they were just a linked list. So we have just one linked after another. It's just a simple linked list to store the data inside of the toast. It's pretty straightforward, no complication. And also the toast is another heap file. So there is no spatial organization. You just have your data where it starts and a linked list there, and then you get the full data. Right. Now we get to the free space map. One of the problems that the Postgres tries to address, and actually all the databases addresses, is concurrency, right? So we don't want one database that can only hold one query at a time. We want multiple queries, clients and everything to connect. But what happens when we have multiple clients accessing the same information? So we need to have a mechanism to solve this problem, right? So most of the database, they use MVCC. They use the multi-version control, so we have different versions of the same role. So every transaction can hold its own version, and we can have literally hundreds and thousands of versions of the same role. And this is one thing, Marco, back to your question. Back, where, oh, no, too much. Back here, where we are talking about the changing addressing the index. Back too much. Oh, actually, it's here. So when we have this information here, when we do an update on the database, remember the database doesn't remove the role. When we update it, the database doesn't change on spot. It's just copy that data and save in another place. When you do a delete, the same. The database doesn't remove the role. The role is there, and it's just marked as removed, right? So the thing is, we need to keep this information apart from those different sessions. So Postgres doesn't have does not use an external file, like, for example, MySQL, to hold the information of the visibility, right, of the row. So the information is held here inside of the page itself. When we do an update here, the transaction that is updating will put his information here. We have the transaction, see the transaction management here, that is doing the change. The transaction, we have the transaction that inserted, the transaction that removed, and the transaction that created the new data, that changed here. So the information is held here, right? And Postgres use that information as well to keep the different fields one apart. So we can have many of the same data inside here. That's what we call bloat. When the same row has many copies of themselves, we say that table is bloated. Bloat, it's bloated, it's there. So the table is bloated. This is what they call, and that also happens a lot often when you have a lot of updates, for example. You copy one table and mark the previous as removed, and then copy and mark as removed. If you have a lot of updates and you don't do anything to clean, that's a mechanism, and all Postgres DBAs, they love it from the deep of their heart, that they call vacuum. It takes care of those cleanups, right? Those housekeeping. So, but the thing is, it's very inefficient to go to all those removed rows to see if they are alive or dead tuple. We need to have something more efficient, right? And other than that, we'll see later that indexes on Postgres, they don't hold this information. The index doesn't know which page is dead or alive. So they rely what they call the free space map. So it's a map that tells what are the pages that have empty space inside of that table. So for example, when we do an insert and we need to allocate space on that table, instead of going block by block and checking which one has space, we go to the free space map. And we ask the free space map. Okay, for example, let's say I need here a slot with 4 slots available. Before here, one thing that it's interesting is the space here is the unity that is measured is every 32 bytes. It's not in bytes, it's 32 bytes. Because they want to keep it to fill in 256 bytes. So it's really small structure here that we have. So every time that we talk in a unity, we're talking about 32 bytes. So here I want to store in this example, 32 multiplied by 4. It is 138 bytes, right? So I want to store that data here. So what the database does is, it goes to the free space map and it starts looking here from the leaf page. And which of the one is the next one that has 4 available spots? Well, in my case, this one has 4 available spots. And then it goes up to the tree. Well, this one here, that's just him on that same leaf doesn't have. It has only 2. So that's not this one. It goes to the right place. This one has only 3. That's not available space. So doesn't make sense. I'm coming down, so I go up. Oh, this one has 7 available spots. Then what I'm going to do, I traverse the tree in this position. So 7 is larger than 4, then I go to the left. Right? And here, this is the page number 6, that I have at least 4 available space. This is how Postgres finds blocks that have available space. It doesn't need to traverse the whole table to find available space. It's controlled by the free space map. Space block, yeah, space, exactly. It holds that information, and it also can also be used by indexes. For example, how do you know the index knows without much effort if a row is dead or alive? Well, it's now about probability, right? If it comes here to the free space map and it's all filled, or there's no, it's likely that that row on that place is alive, is not dead. Because if it was dead one, it would be cleaned by vacuum. And that's why it's about probability, right? But still, the index, in the case of the index, it still needs to go to the data file, the heap file, and to catch that information, right? Well, yeah, but this, it's usually in memory because it's really tiny. But you do every transaction, yes. Yeah. Yeah, the free space map, yeah. Well, when you move to another page, yes. But if you don't move, that's it. Oh no, yeah, it will. Well, eventually. Oh, you mean this data structure? Yeah, yeah. You need sometimes to do rotations. Yeah, it's just normal another tree. Yeah, one record with needs, let's say, 4 bytes. Yeah, yeah. Exactly. This is the block that you have at least 4, exactly. No, they do not split. They create a new page. Yeah, they create a new page. In that case, if you like, let's say you have 9, you need 9. There's no available for 9 here, they're going to create a new space. Or in your example, you need 6, so you have 2 here and 4 here. No, they do not split. The information, the data is not split between blocks on Postgres. If the information does not fill on that block, for example, all of them being filled, we create a new block. If the information cannot be held inside of the block, is larger than the block, it goes to toast. So the data files, the blocks, they never split information. We always hold the whole information, let's see, inside of the block on Postgres.
This is more about what I'm trying to say is that if there's 6 rows between
Yes. No, it's not 6 rows. That's a different thing. So let's say, yeah, you are talking about transaction, right? You have one transaction that you need to insert 6 rows. So if you try to fill together, if they, in that case, yeah, the rows will go to another one. Yes. All right. Now we're going to talk a little bit about table access. So now that we have some understanding how the data is being stored, the data needs to be accessed somehow, right? So there are a few different ways to access the data inside of the database, inside of Postgres. And one of them is to access through indexes. Another is have direct access. And when we have direct access, we're going to see that we also have a couple of ways. And before we jump there, one question that we should ask is, what is an index? So an index is really a simple data structure, basically, that we have on the database that helps us to find information faster. Index is basically created to help us find something faster, right? And as the documentation says here, indexes are a common way to enhance database performance. That's it. And when we say that database performance, we're talking about lookups. Because we see that index can hurt performance, and they will when we're talking about updates, insert, and all this kind of stuff. Because remember, as Marco mentioned here a couple of times, and he's really worried about the data, the right amplification. So every time that we change something, we need to update the indexes, right? So they do not come for free. They serve for one purpose, that is to enhance lookup performance. That's basically what they are for. So how can we access data inside of Postgres? The basic and most common method is using a full table scan or sequential scan or SIG scan, the way Postgres calls this one. That's the basic method, the easiest way for the database, and the cheapest way. Because when we traverse a table on Postgres, it does do a sequential scan. Remember, the file, the heap file, is a sequential piece of data. So I try mostly to do a sequential scan. So it has no organization. And remember, when we do inserts or updates or deletes, there is no guarantee that we're going to keep the order for the data inside of the tables. And the select, they reflect those things, because the select on Postgres, when they use a sequential scan, they just go to the table and get the file, the information. No order, not at all. For example, here I have a couple of tables here. Postgres, as I mentioned, it can do parallel queries. You can split the queries and work in parallel. I don't want it for now. I just disabled that feature here on my database because, well, I do want to go for the slow thing, the sequential scan, right? So one way to understand, to see, is when you do an explain on the database. Can you all see here? Let's. Nice. So basically what we had here is a sequential scan. On the table, I call TB access. This is the name of the table. I know it's not the best name for talking about access things, right? But yeah. So it did a sequential scan here. So what it did, it went to all the rows. And let me go to my example. So see that I have a filter here, ID 1500. It's telling me that it has a filter here, and it needs to remove 1,700,000, a lot of rows. It had to read that many rows and remove all of them to keep what I'm looking for. This is a sequential scan. It goes, read the whole table, get what you asked for. In this case, I asked for ID 1500, and then send that information to the application, right? In this case, it's really bad, because, well, I need to read like 2 million rows to get one of them, right? But the database has no way to know if it only has one, because heap file doesn't hold any information about things. Remember, it's just one thing after another. So the database has to go all of those rows and checking if there's more. So when we are reading the data, it's gonna put the data in memory, right? So if I have enough space, if I don't have enough space to keep in memory, it's gonna save on temporary files and split to internal loops and going to that. In my case here, it was not as that bad because, well, I have enough memory to keep all those things. So you can do in one batch, in one row, get all the information from the page, put in memory, and then scan those things, all the blocks, right? If I don't have enough memory for all the blocks, let's say I have memory for half of the blocks, it needs to loop twice. It gets the information that needs, create a temporary file or discard depending on that they were looking for, and then goes to another batch. Keep in mind, guys, the CPU cannot work with data on disk. Actually, the CPU cannot work with data on memory. CPU only works with data in cache. But memory has a physical directly connection to the CPU. So the CPU can go to the memory, get that data, put in cache, and it's registered and work with that data. Every time that we go to the disk, it needs to be loaded from the disk, physically put on CPU, for CPU to be able to access, because the motherboard doesn't have physical, literally physical direct access from the CPU to go to the disk. Who does that is the memory controller. So that's one of the reasons and performance, obviously, that every time we need to go the data from the disk file to memory. So yeah, this is the sequential access, right? So even though it was expensive here because it had 2 main rows to read, it's still cheaper to go through a complex data structure, like, for example, an index, right? So the scanning is done to the buffer cache. That's the loop stuff. So if we have enough space on the buffer cache, the better. So it's used a small ring to prevent larger tables from abusing the buffer. So if we have a table that's too large and it can fill the whole buffer, so then we have different problems, right? Because we can have cache eviction from the buffer. So no one wants to have one select, a large table, and clean up the whole buffer because of that select. So it has smaller buffers inside of the buffer to try to not make them to abuse. And if another process needs to scan the same table, if we have a concurrent process and they need to scan the same table, the database will check if that information can be reused. So if you don't have a transaction, for example, that's changing that data, that invalidate the cache, so it can reuse that's been there already and can join the different caches so it doesn't need to go through the disk again. So it means scan does not necessarily start from the beginning of the file, right? So if we have those information there. And sequential scan is the most effective method for scanning the whole table because it's just traverse sequentially. And sequential scan is efficient when having low selectivity. What is low selectivity? No, that's low data. No. Anybody? Low selectivity?
It means that you're selecting a large number of the rows based on the data.
More or less. Uniqueness. You don't have uniqueness, exactly. So let's, for example, you have a column that's true or false. It's worst case that you can get. Because if you have 1 million rows, you have only 2 different types of data. How can you get an index efficiently working on 2 types of different? We can get. We're going to go that later, that we have some data structures that we can be highly efficient to work. But this is what means selectivity, low selectivity. So when we have low selectivity, the most efficient thing to do is scan the whole table, right? Because, well, you're going to get them anyways if you go to an index, because you're going to get most of the data. And there's really more efficient. So the next one is what we call index scan. The name might be obvious, right? So it scans the data through the index, right? But even though the name is obvious, not all indexes on Postgres are able to use index scan access method. We'll see what does that mean later. So using the index scan is basically the full method that a B3, for example, gonna do on Postgres. So how it works, it let's say we do a select. Let's try back here again. So I'm just going to create an index right on that table because I need an index for an index scan. So if I do a select here for this table, oh, but before moving, you see I'm running a explain analyze. An explain analyze runs the query itself. It does not only do the explain. And we have down here the execution time, right? So we have the planning time. It took longer to plan the query than execute itself, right? Sometimes it happens. The previous one, look my execution time. 235 microseconds. Actually, milliseconds. This is 0.3 milliseconds with my index. So in this case, it's a lot faster, right? So well, how does that work? Let's say instead of doing this select here, I do a between. Thanks to, so I did a between, right? I select more than one row. This is easier to understand. So here I have 400 rows. The index scan access method, it goes to the index, find the row, and then get the address. Remember that address that we had there? We call PostgreSQL called tuple identifier, TID. It gets the address and then goes to the block and get the data. Goes to the next one on the index, goes to the data file and get data. So it doesn't get all the data from the index and then fetch all the data from the table. It goes one by one from the index to the data. So it's a bit inefficient in the sense when we have the index scan. Even though it's a lot better when we have a small amount of data that we're selecting, like one ID or a certain number of ID. It's a lot faster, a lot better than the full table. Yep.
So it's a tuple point. So
yes.
It should point to the A key page, right?
Yes, exactly.
And then from that page, it gets the header, and then it will go to
Yes.
item, right?
Yes.
But what is the tuple pointer then? Is the index stores more than just the page?
No. This is the address of that tuple pointer. This guy here is exactly the tuple, the TID, the address, because it's literally the physical address, the order inside of the page, right? Let's say here we are on the page number 5. On the page number 5 here we have 3 rows. Not 3 rows. Yeah, 3 rows. We have 3 rows, right? So this is the row number 1, row number 2, and row number 3. In the index, you're going to have the row number, the page number, and the position of this guy. So going to be 5 and 2, for example. Let's say we're looking for this one. This is what we get from the index. So the index is going to give in the address. Well, look, I want the row that's on the page number 5, item number 2. And then the item number 2 will point to something of those guys. And then the database will fetch the information from those guys here.
So then it will go to the page.
Yes.
Check what item corresponds.
Exactly. Item will yeah, yes. And inside of the item, you have the physical position here in bytes. Okay, which byte we start and which byte we end inside of the item there. So yeah, it does the seek. But this operation already is done fully in memory. Like what goes from the index to here, the optimization from the index is the index will tell you which page you need, right? So then the database will fetch only that page, that block from the disk, we'll put in memory. And then from memory, well, it's already memory, works in memory, and it's 8 kilobyte block.
So if the index goes there,
Yes? Yes? Well, when it's moved to another page, the index is updated. Remember that the cost for update to move into another, the index is updated. What can happen is you delete. The database didn't have time yet to run the vacuum, right? The index was not removed. So you do the select, you go to the index come here and here, oh, it's deleted, it's removed. The database will discard. No, it's a deleted, it's just discarded one, yeah. It did. That's a problem when, for example, you have bad vacuum configuration. And when you have too many bloats. So when you tell people that when you have too many bloats, it will slow down your database, it's not because you have much data inside. It's because now the database does extra work for nothing. It will not result. It is marked as a removed. The database will not return it. It will just ignore that one. Yeah, it will find, it will read. It will not return, Marco. It will not return. That's the point. It's just like you go for MySQL, you are reading data, that's marked as removed. Or you have another transaction that does not have visibility for that data. If your transaction does not have visibility, the database you just ignore. You not send it to the client. The same, if you have marked as removed here, the database will still come here, and when you see, oh, it's marked as removed, and you ignore, it not return to the client. Yeah, you delete. Yeah, you get no. Yes. The same. Yeah, here you also know that it's deleted.
Yeah, but you know that there is move. When you have split merge page, right? You have the split on the page, and you take this on the first page. The pointer of that new page is present, so you can find it. In this case, I cannot find it.
Well, you need to attend the other talk. The thing is, okay, let's the worst case, the vacuum is not running, right? So the index is pointing to the old table, the old tuple here, right? So the index is pointing to the old tuple. We did an update. It will point into the old tuple here. In this tuple here, you have the address for the new one. And it will point to the new one. If you have another update, you're gonna have all the chain, exactly. Yeah. So when the vacuum runs, what the vacuum does is the vacuum come here and clean those pages and update your index to the final one.
But that could be happening if you have a movement where the data is.
No, because it's isolated inside of the transaction.
May I summarize the MVCC how I understand it?
Yep. Yep.
So there's no readable, there's no unreadable. Everything is here.
Yes.
So when you have the new transaction, so first of all, it's also copy for
Copy and write. Yes, copy and write.
So it's not doing anything in place. It's not doing update in place. It's
No.
what the user
Yes.
and then put it there.
Yes.
Then the transaction ID will be associated inside of that jacket.
Yes.
So there's no readable, right?
Yes.
So then MVCC will be implemented by just storing the previous versions of
Yes.
records, right? And there should be some mechanism to basically implement the isolation level,
Mm-hmm.
right? So this
Indeed.
is that I don't know.
Yeah, it does. Yeah, the isolation level also plays a big role here. So let me do one thing. The thing is, we had one less hour today this year than last year, right? So let me just hold on. where's it's here? Okay. GitHub. Altino. Last year was 22. Let me see if I have this one here. Yeah, this is a SQL file. All right. So let me just create some extensions here, and let's try to go through your questions pretty quick. So I don't have the visibility map here. Nice. I'll have to compile with the extensions here. Okay, I won't be able to show you what I want to show you, but let me try to go through the explanation here. So, oops. Is it? So, the isolation level, they do play a long, big role here when it comes. So the transaction management here is held inside of the page itself, the block itself, right? So we have the transaction that created the role. So when let's say when we're doing search, we're creating a transaction, we're doing search, that transaction ID will be held here, and Postgres uses the transaction ID as a timestamp. The transaction ID is sequential. It's not random, it's sequential, right? So it's gonna use this as a timestamp. Let's say I have the transaction ID number 10. Because I'm inserting the row, it will tell me the only transaction ID that can see this row is the transaction ID number 10, because the transaction is still in place, it's not committed. So the other transactions, they'll check here, oh, what is your transaction ID? 11, 5, 15, whatever, doesn't matter. Is transaction ID number 10? No. So you cannot touch or see this row. It's invisible, right? Because on the if in the logic, it cannot see here this row. So let's say we committed a transaction. So now it changed the state from the transaction that is committed. But we still have the transaction ID number 10. Remember when I started the transaction ID number 5, this row didn't exist. So depending on the isolation level, if it's for example, read committed we'll be able to see because we read committed. But the repeatable read won't be able to see this here. Because when we started the transaction ID number 5, this row didn't exist because the transaction ID 5 is lower than the transaction ID number 10. So it's implemented as a timestamp. Now, all the transactions that start from this point, 11 and 12 and 15, they're going to be able to see this row here because, well, they are on a timestamp larger than the number 10, right? Let's say the transaction number 15 didn't update. So until it doesn't commit, what it's going to do is copy this information here to somewhere else, and it'll create another transaction ID number 15. It's not committed yet. Again, nobody else can see, because the transaction is not committed, and only the transaction ID number 15 can see that information. So the moment that transaction ID 15 commits, it will lock this guy here, put a lock, mark as removed, and then mark the transaction ID number 15 as committed. So these will now don't exist anymore, because inside of the if, we'll check, is this removed? Yeah, it's removed. So the if is gonna be false, and then the transaction only be able to see the row on the 15, unless we have the isolation level, and some transactions already started with that isolation level. So the transactions that started, they are lower, smaller than the number 15, right? So we have the timestamp there. So it uses the timestamp here to see and to keep the concurrency. depending on the isolation level. So yeah, it's a role that's played together with the isolation level and the management of the transaction IDs to the database. Mm-hmm. Everything is a transaction on Postgres.
If I don't do start transaction.
Everything is a transaction on Postgres. If you look at the database, you are doing a transaction.
So it will generate the transaction ID?
It does.
And what is the timestamp there?
The transaction ID is used, the ID is used like as a timestamp. The idea of timestamp is the transaction ID itself, because it's sequential. It causes another problem. Every solution has another problem because it's a 32 bits integer, the transaction IDs. What happens when you run out of 32 bits? You come back to the beginning. That's what they call in Postgres transaction ID wrap around. So if you do not have, there is a mechanism to freeze those transaction IDs. So just a flag they put there, it's frozen, and then it restarts the transaction IDs all without those flags. So it has a mechanism to, the problem is if you do not have the vacuum running, the database, they will stop. The Postgres, the new versions, they won't let you mess up with the data. They'll just stop until you fix the problem. But you can still force. If you want to see that happen, you can still go there manually force. So what happens is it goes back to the transaction ID number 1. So now, the transaction ID is a timestamp, right? If you are the number 1, what happens to all of those? Are invisible. Because you are on the number 1, so there's no more, there's no number 2. There's no number 5. You are on the number 1. So you basically, not physically, but logically lose your data. And you can mess up with all those things if you keep committing. Yep.
So there's no other modes for the database itself?
No, it does. It does. It implements different types of logs. Yeah. Oh, you mean logs? sorry. No. No, it does. The only log the database does, the physical log, is the write-ahead log, the log files. So basically, to keep consistency, yeah, this is the log that we use. But for transaction of those things, no, it doesn't keep those things on logs, right? Marco, could you get a water for me, please? So back, okay, the index scan, as we saw here, it has some inefficiency, even though when we are selecting a small number of tuples, small number of rows, it's very efficient. So, but what happens if we want to select more, like a larger number of rows? Well, what I was saying, another problem that we have on the index scan is high correlation. Thanks. So we talked about selectivity, but there is this, they call correlation. What they call correlation on Postgres is how ordered or how chaotic is the data inside of the database. In this example here, I have the data, the IDs, for example, close one to another. I have an index here, and physically, I'm speak physically on the disk, they are close one to another. This is the best situation, because when we do a select, like this one, that I need to have more than one block, just because the data physically is close one to another, so the chance that the next data that I have is exactly the next block size on disk that I need is pretty high, right? So here I have a high correlation of the data. But it can happen when we have a lot of updates. Remember, the updates, it moves the data between the blocks on Postgres. So the correlation, they can get a little bit chaotic. The problem about low correlation and the data to be chaotic is now for the same select, instead of having 2 blocks, Now I may need 3, 4, or 5 blocks because I have one row on the block number 5, another row on the block number 17, and then then we need to read more blocks, and the index needs to go and come and go and forth a lot more often, right? So this is what happens when we have your database super slow and someone say, run a vacuum full or recreate your table. So what does they do is they reorganize the table, improving the correlation. And magically, we have a performance improvement. The index is still the same. The data is still the same, right? Didn't change. But how it's being organized on disk has changed. And even the memory consumption, they can go down a little bit because now we need less blocks when we do the same select. So in other database like MySQL, they call data distribution, right? So just to get different words. So we also need to be careful when we have those different types of distributions, especially when our database is run for a very long time. We have a lot of updates and things. So the data distribution, this changes dramatically, and it goes down. Okay, now we are to the index-only scan. Do we have a break? Do you guys know? I didn't check. Because I heard like people walking. I don't want to skip. Okay, yeah, then let's just finish this one. We'll have a 10 minutes break. So I know it's too boring. Let's walk a bit. Okay, the index-only scan. So some database, they call it differently. They call covering index, right? And it's very appealing. So an index-only scan or covering index happens when you do a select and it only needs to go to the index. It's really, really efficient because you don't need to read the data file, right? It's pretty cool. The problem is you need to have the data inside of the index. There's no magic. So if you don't have the data inside of the index, you still need to go to the database. Let's try to do here. And remember that I created an index here on ID. Let's try to do something better. I'm pretty much sure I created an index on ID and name. It doesn't seem to happen here. Okay, let me do this now then. And there's something else. Okay. No problems. Oh, I'm giving the same name. IDX2, for example. Okay, so now I have an index on the ID and name. So if I select ID and name here, it's going to do an index-only scan. So it's faster than going to the table because it doesn't need to go to the table. It only goes to the index. See, it just read nothing. Yeah, it's a covering index. Yeah, that's what I mentioned. So it's a covering index, right? So it doesn't do anything. I mean, it doesn't go to the table. Even if we go here in the range, for example, my tool sometimes plays, where is my select? Here, okay. So the same, we have here, and the amount of data that needs to collect is pretty small, right? So it's a lot more efficient. The problem is now we have a larger indexes. The problem for larger indexes is that we always need to update them. So when we have index only on the ID, if we do an update, for example, on the name, and it's hot, like on the same tuple, we don't need to change anything on the index. But now we have an index on ID and name. So if you do an update on name, now we need to update that index as well. And if it changes from one block to another, we need to update both.
So where is it physically, the index? They're part of the same.
No, it's a separated file, physically separated file.
It's a different file?
Yes.
Yeah, it's using a different format.
Sort of. The organization is basically the same, is to have 8 kilobytes blocks, but then it's in this case as a B3, it's a B3, right? So yeah, it is. But the blocks, the size of the blocks, they're still the same. They're all the same, all along. So, but yeah, in this case, the inside organization is not heaped up anymore. Now it's a B3. Move on. Almost done with indexes. I mean, in the table access, we have the bitmap scan. Remember that I asked, what does it happen if we need to select some information from the table that we have a lot of results? It's not efficient for an index, right? Because it needs to come and go to the index, get one ID, and then go to the table, go to the index, get one ID, and go to the table. It's not efficient. So to solve that problem, Postgres does what they call bitmap scan. So it goes to the index, find everything that needs to be found, and then it creates a bitmap with the positions of the data on the data files. And after that, it goes to the data file, gets all the blocks, and map with the bitmap that has been created. So it's an improvement on the index scan access, but now doing in only 2 loops instead of many that we can do. And another important usage of bitmap index is when we have 2 different indexes. For example, some database, they cannot use 2 different indexes on the same select. They either use one or another. Postgres can use 2 or more indexes. So let's say we have here, let me just drop that index because my next example will for sure use it, and I don't want. This is different from having a 2 columns index. Come on, 2. Okay, I dropped the index. So I have 2 indexes now. I have the index on ID and I have index on name, right? If I do the select here, where I only use name, obviously, it will gonna scan. Here is the name of this index. But you see here, it did a bitmap index scan. Why? Because my selectivity for that name probably is not enough. It needed to get too many rows from that information. So in that case, it's better to use the bitmap index scan. So it goes to the index, it gets everything that it needs, create a bitmap, literally a huge number of bits, zeros and ones, and then it check, oh, is this in this block? No, 0. Is this in this block? 0. Oh, this block, yes. Block that is, and then it fetch the block related to that position that we have that information. No, the index is normal. The index doesn't change. Just the way to fetch the data that changes. It's a normal index, it's normal B3, nothing change. It gets all the IDs from the B3, and remember that the ID has the block size, the block number. So it creates a bitmap with that block number. Because it will get all those blocks, only the blocks that it needs in one fetch. No. we don't store the vector. This is created in memory. It's just process, just CPU. That's why I say the index is the same, doesn't change anything. It's just a normal index. It's just the access method, the way to access the table that change. The index doesn't change anything. Like, this is still the same index we created. See, it's still the good old plain B tree. There's no difference. And the same when we use here let me just increase this thing here because it's annoying me. I hope it has enough space. So when I use this, still more. I need to disable this more here because I every time need to type Q. So here I'm using two indexes. The first one is using the string to find the name Kelly, and the other one is on the IDX, on the ID, the indexes. It uses the two indexes, just like normal indexes. So, and then it combine those two indexes using a bitmap. In this case, a bitmap OR, because I use it OR here. So it uses both indexes and then create a bitmap with them and just combine the tuples and send back the result. And if we have 3, 4 indexes, we can even get the result of those two and combine with another one with the bitmap. So the strategy of using bitmap indexes is highly effective and efficient when we're doing indexes, right? One thing that we need to be careful before we move. So it needs to create a bitmap in memory, right? So now we are using memory to improve performance. The thing is, memory has limit. We don't have infinite amount of memory. So when the bitmap starts to grow too much, what the database does, it's converted to a lossy style. Instead of holding the ID, the address, it only holds the block. And one thing it needs to do an extra work. Let me see if it have here. I don't have here. I think this one I do have. Nope, I don't have this example. Yeah, this one I definitely will have. What I want to show you guys is, what is this? We have loop. See this recheck condition? So the bitmap for resolve this query, it got too large. What they will do is, instead of hold the full address, it only gets the block size, the block number. So it fetches those blocks, and after get all those blocks, it will internally do a second check for this condition here. So put all those blocks in memory, so we don't need to do extra I/O, so it saves I/O. But in memory, it needs to check inside of each block to get the data. This is what it means to have in this recheck condition, right? Data to fetch, yes. Yeah, like in the example here that we went for one each, yeah, no, like a few here, but here I'm reading 1,500 rows from that table, yeah. Mm-hmm.
Is there a way to figure out how many blocks this recheck line can? Because it's kind of a two-level schema, right? Not two-level schema, but it's more like a strings. You have probably 100 blocks, and this recheck condition is block.
Well, you're gonna get those blocks anyway. Remember, you're getting the data from the table, right? So you need to read the block, even though you get only one row, you need to read the whole block. So the difference here is when it is smaller, it gives you the full address. It's like, okay, you are coming here to the hotel, you give your full address, road name, block number, and everything. The difference is now you only know the road name. You don't know the block number, but you still need to come to this road. Right. Yeah. Yeah. From the I/O perspective, it doesn't change anything. It's just a bit slower because now you need to go inside of the block and do the check inside of the block, right? Another loop. Yes, bitmap. Yeah, lousy bitmap. And we're done for the access type. Let's have a break before we come to the join operations. Have some coffee so you guys don't sleep. Joins is one of the key features in the database, right? So I can't think of the database not having joins. And Postgres is the same. And on Postgres, we have a few ways, a few methods to do joins. The more common and traditional one is the nested loop join. This would be the table scan of joins, right? So is the easiest one to do, the less efficient, obviously. And as the name implies, we have loops and they're nested, right? So they're combined. So basically how it does is it reads one table, picks a table, usually the smaller table, and then for each row that it finds, depending on the selectivity, on the where clause, it will loop the other table. Let's say we do a select here. In our example, we do a select here that reads 1,500 rows. So here we have 1,500 rows. If we join this table, let's just drop my indexes again, because I don't want them to play a role here. Yeah. So I want to do a very simple thing. Select from table, access A, join table access B, on A.id equals B.id. Oh, obviously. So what we have here is a nested loop. Awesome nested loop. So here, if I have 1,500 rows from the first table, it's going to go for the second table 1,500 times. And do a full table scan 1,500 times. Pretty cool, right? Highly efficient. This is what a nested loop does, right? So if you do a select between two small tables, that's fine. But if you do a select on a larger table and you see something like nested loop, that's pretty bad, right? That's pretty bad. So we need to do something. That's not what we want to do. Well, the next one is what we call a hash join. So as the name implies, a hash join, it builds a hash table, right? So when we do a select, it will pick one of the tables and build a hash table. But to be able to do a hash join, the tables, they need to order the results. And the tables need to be more or less at the same size. So what it's going to do is, okay, it pick one of the tables, the one from one of the side, the conditions. You create a hash table, and then we'll loop the other table. We still have a loop here, but instead of 1,500,000 loops, as the previous example, we're going to have 2 loops. The first loop is to create the hash table, and the second loop is to find the row. So it gets all the IDs from the second table and check with the hash table that has been created. And compare. Oh, is this here I'm looking for? Yeah, so then it goes to find the result. If it's not, it's just discarded, right? So it's a lot more efficient, especially because the hash comparison is highly efficient, right? So if we go for the big O type of things, it's old one, right? So it's highly efficient algorithm. So internally, how it works, the Postgres, the database, the algorithm will get the table and split it in buckets, in batches. So if you have a larger table, it will split in smaller batches, smaller buckets, to create the hash tables, or smaller hash buckets, instead of have one huge hash table. That's for memory optimization. Remember, the database will always try to keep the large tables not using the whole buffer cache, right? We don't want the whole buffer cache to be filled. And you may still ask, what happens if the table is too large, that even having those buckets, they do not fit in memory? I mean, in the space, there is a space, there's a configuration that we get to the table. That is the work mem on a Postgres to work with those things. Going to work with sorting. So if it doesn't fill in that space, it will create temporary files. And it needs at least 2 temporary files for each batch. One for the hash itself, and another one from the data that comes from the second table. So when it splits all of them, it starts the comparison and builds the result to send to the client, right? And we can actually kind of see some stuff. Let's build 2 more nice tables. I think I already have them. But just in case, yeah, I do have them. I didn't drop them. Here's another nice example for our nest loop. So as you see here, the nest they did. And for the hash table, one thing that you can do, we can enable to log the temporary files. I've just enabled here to log the temporary files. Let me try to get, where is my mouse? No, it didn't move. Come on. Is that fine? Can you see? All right. So jokes aside, I have here data, db, pg, 15. I have my logs. It's not exactly what I want. -F. So we can just start logging what we do here. And I'm gonna just use this example Let's run my explain. Okay, as we can see here, we have, it's a different join, indeed. Oh, I have indexes. Indexes are nice when you need them. Okay, I don't need you, I don't need you. Let's hope for the best. Yeah, now we are getting that. So I have a hash join here. It's not as bad. See, it's creating buckets. In this case, it created 36,600 buckets. This is the memory it used. So I have by default, the work mem is 4 megabytes, if I'm not mistaken, in my case. Yeah, it's gonna probably do around 4 megabytes. And that's the memory it used. Everything that goes beyond the memory, you're gonna create temporary files. And in this case, I have a lot of them. Trust me. See, I do have a lot of them. So it will use that memory. If everything is done in memory, obviously going to be a lot faster. But here, because I'm selecting too much data, they cannot fit my work mem. So the database is creating the temporary files. And obviously, this join would be a lot more expensive and would cost a lot more time, right? And just out of curiosity, here I have 1 million rows. Yeah, it did. And if I did at least it was not the awesome loop, right? Because it would have to loop the table 1 million times. It didn't have to do that much. The logging? The hash? Then it's by default. The optimizer will try to choose the best join that you can get. One important thing, we don't have indexes hint on Postgres. Remember? We can trick the database, though, to use or not the index we can use. There's a lot of way to trick, and that is a whole new talk. But yeah, there's many ways to trick the database. And just for example, last year I just created a challenge on LinkedIn that I gave people 2 tables in a report that I wanted them to write a report. So those 2 tables, they didn't have any index, and the challenge was to create the report running in less than 2 seconds, because the example that I gave that was running in 2 seconds without creating indexes, only plain select. We got some answers, some they created in 1.5, 1 something, and then I challenged them again. Can you guys do in less than a second? Because my select now, it runs in 700 milliseconds, 0.7 seconds, without creating index, only with selects. A guy run it in 85 milliseconds. He did a query optimization from 2 seconds to 85 milliseconds with the same data without creating any index, just tricking the database. With indexes, it went to 15 milliseconds. So, go back there, we have now the merge join. So this is the best case that we can get. So, because that one gonna use indexes. This is what the one that we saw here. After creating my indexes, where are them? So what the merge join does, the merge join it gets two ordered sets of data, create bitmaps, and join them. It's as simple as that, right? Use two ordered lists to set. The data set may be pre-ordered using the index, and that's why it's highly efficient using the index. There are some cases and circumstances that even not using index, the database can still do a merge join, but they are rare cases. So if you want to get a merge join, you probably will have to go for an index. So it will get those ones and join them and merge them, those results. Right? It's highly efficient. And the thing is, a merge join, the result of a merge join, it can be used for another join. In this example here, only joining two tables, right? If I had another table, if I have a third one, that depends on the result of those join here, the database would also be able to. What did I do? Oops. Am I in the right place? Yeah. If we had a third one here, the database will still be able to use that one, the result, to merge as well. I probably have something here. Let's take a look. See, here I'm joining three different tables: tickets, tickets flight, and boarding passes. And it just says it doesn't exist because it's not in the path. Now it's in the path. See, we have a merge join between the tables, the index ticket fly primary key, that's from the tickets flights table, and it's joining with the boarding passes here using another index scan. All of those are built in the index, they didn't go to the table yet. And then they use the result of this merge join and do a merge join with the table tickets. We have a cascade merge join, and all those are done by using the indexes only. The only table access happen after this finish here, and can do a bitmap index scan. It didn't show here, but yeah, it will probably do a bitmap scan on the table. So that is the most efficient case when we use indexes. When it happens in the merge join. And also it also does merge join and helps when we're using order by. The database can use the index and the merge join, so to order the result and to return to the database. And remember that I said that the database can do parallel joins and parallel selects. So most of those joins, except the hash join, they can be done in parallel. So even the nested loop, it can do in parallel. So it helps a lot. It helps improving performance. And we can sort of control. Remember they've been disabled here. No, here, yeah, it was here somewhere. No, here it was on the one. Yeah, so in my case, I just disabled here for the parallel joins, so it's not doing the parallel queries, because I told them I don't want to. I want the parallel gather 0. So the fact that they have it enabled doesn't mean it's going to do all the time. There are some circumstances that it's able to enable the parallel. And one thing that we need to keep in mind as well, it's parallel query is not necessarily all the time efficient. In my case here, I do have parallel scan. See, I have 3 workers that have been planned, or 3 threads, let's put it this way, to do the parallel scan, and 3 workers, 3 threads been launched. So it is split in 3 guys doing the work. And do you remember that it's around 200 or 600 something before? Now it dropped to 94 milliseconds. So the performance doesn't increase linearly because it's IT, right? Nothing goes linear in IT. And in some cases, having parallel queries can hurt the performance as well, especially when we have high concurrency database. If you have your database that has 128 CPUs and you put 1,000 connections and every connection using 10 threads, well, that might not be the best for your database, right? So we need to be careful when using those things. When used properly, they do give boosted performance improvement, but when not, they will instead hurt the database performance. And now, not yet. Yes. Mm-hmm. Yeah, it's independent. If you join, like, they treat the tables independently. So even though, like I did here, I join the table with itself, I'm pretty much sure I did somewhere here. Here, yeah. So if I had here those indexes, I probably have those indexes here, right? Say that we have the tables here, they really work like independent one. It launched 3 for the first table, and then to get the information for the other table, it also had more 3. See, it did parallel scan. And if we're using index or something like that, that enable the bitmap, yeah, they use as well. So even though they are the same table, the database treats them as just independent ones. It does not necessarily mean it will get the data from disk, because remember when we were looking before, the database can still use data that's been fetched that is still on memory, still in memory. The problem here in my case, those tables are too large. So they need to be fetched from memory, put on the buffer, and then eventually they're going to be evicted from the buffer. So when the next table comes in, that data is not in the buffer anymore. Right? And in my case, probably we're going to read the same table twice, so which is highly inefficient. And now, finally, indexes, right? That was supposed to be the topic of this talk. So, when it comes to indexes, we need to understand, and we know one thing, what they call operator classes. Those operator classes, they're very important. They're actually quite simple. The operators are those things here that we use to compare something. Equal sign, larger than, smaller than, between. So those are what they call operators. They're going to be used to compare 1 or 2 different data. So in some cases, like the equals, you have data in both sides, right? The large, then we only have one side comparison. So those are the operators. And when we create an index, they can be created in Postgres. We don't need to only stop with the index that we have in Postgres. We can extend them and build new indexes when you create an index or when you use an index in Postgres, we need to tell them, okay, what operator I gonna want? I want to work. And I need to tell the Postgres which function this operator gonna use. So every time that we do a comparison, like for example, on an equality comparison using a B3, the database will check internally, okay, which index are we talking about? Oh, it's a B3. Which operator are you talking about? Oh, it's an equal comparison. Oh, it's an equal comparison. An equal comparison requires data from both sides. Okay, what is the type I have on the left hand? It's an integer. So then I expect another integer on the right hand. If you don't have, we have a mismatch type. Sometimes the database is able to work around on this mismatch type. The problem is when the database works around on the mismatch type, it will not use the index. Sometimes you create a really nice index, it's been working since you created the database, and eventually one application complains to you, it's not using the index. All the other applications are using the indexes, but that specific one is not using the index, it's doing a nice nested loop on the full table scan. You go to the database, you check, nothing wrong. You run in vacuum every day, it's everything fine. You try to select works. Right. Must be something with the application, right? And then you go to the application, the guy is comparing an integer to a string. A quoted number. That's a string. In that case, because of the implementation of the function here, that the function expects, and for the database to be able to work around, we need to have a function with overloaded parameters inside of the database that expect an integer and a varchar. And that function will not use the index on that circumstance. Another circumstance that happens is that operator is not implemented with that type. So, for example, if we're gonna do working with JSON, and we want to do a select with JSON, it's the operators that the index type we usually recommend to use with JSON, that's the GIN index, they use those funny operators. Sometimes you have at, sharp, and we need to go there and to try to understand what they mean. Oh, that might just be an equal comparison. It does have to do with car set, yes. It's also because the way that they are implemented in Postgres are extendable. We can overload, for example, we can write here our own function to overload the equality operator for B3. Using, you don't need to use C, we can use the plain PGSQL, I forgot the name of the language now, the PGPL SQL. We can use them. We can use PGPython, PGPerl, whatever language database supports to write them. So, the operator classes, we can specify them when you use an index. Most of the time, we do not specify them. Most of the time, we just do create an index, right? Like, for example, B3. If we go for the documentation, we see that even the B3 index, it has different types. And it has different classes. And we have some classes on B3 that work better with different types of car set comparison. We have classes on B3 that they do comparison, that they do not compare the case, if you add uppercase or lowercase. So we can create an index with an ops type there that just do not compare the case. I've seen a lot of developers, they're doing fancy stuff, they're doing a lower on the application side, convert that to lowercase, and then before they do to the database, or they always save on the database with lowercase. If you use the proper operator class, we don't need to do those things. The database does all of those for us.
So when you create a type,
Mm-hmm.
you create some code.
Yes, we need to, when you create a type, we, for example, those are different things. We have the operators, like the operators are the equal, the large, and we have the type, integer, varchar, and things. On Postgres, you can create both. And when you create both, yeah, we need to code something. For example, when you create a type, let's say I want to create another numerical type, I need to tell the database what are the functions to compare those different types, because you need to an equal comparison. Are they equal, or are they smaller or larger than? So you need to create at least those 3 functions and tell the database, okay, every time that you see this equal comparison, use those functions. And it will send to that function the values that you have on both sides, right? In this side here, 1500 on the right side, and the value of the ID on the other side. It will send the function, and the function gonna send you, in this case, is it equal, true or false, right? There is this whole architecture to create them. Yeah. So it's very extensible. We can create both of them. And then we can create our own index type as well. We can reload them, we can overload them. Like, well, the types, it's overloaded, right, already, because when you do different types of comparison with different types of data, so you compare in a different way. We compare integers is different to compare strings, right? And compare strings different on the car set, right? So you need to overload them and to have different types of comparisons. Yeah, as I say, we can create those types here, so that the common create type. And this is the main thing that we need to understand when we're working with indexes, is they do have the classes. The best way to go is to go for the documentation and see what are the classes that we have to use them, how to use them on the proper way, right? And what are the types of data each class they support. And when I say class, I'm talking about these guys, this equal sign, this larger terms that I have somewhere here. Right, smaller than, those are what we call operator classes, because those are what do the comparison, what the index does, right? Okay, and as I mentioned, we can even implement our own indexes type, and Postgres already has few of them by default, right? So we have the good old B-tree, that is the default for the database. If you just create an index, Postgres will create a B-tree index for you. And there is the default operator, the default class of operator. So that's usually good enough for most of the cases. But there are some cases that we need something better, right? So the B-tree is just a tree. It organized internally with 8 kilobyte pages. All the files in Postgres, they have the same page size, indexes, the free space map, and everything. They have all 8 kilobytes page. And remember, the only way to change them is on compilation time. And remember again, I do not recommend that. Please don't do it. If you do, have a really, really, really good reason to do, because that might be a nightmare later. This is basically how it's basically going to work, just like an old good B-tree. So on the same level here, they have links on the both sides. And in this example here, I'm doing aware that I want everything that's larger than 25 and smaller than 64, them included, right? So it starts on the root Okay, 25, larger than go to the left. Then you go through here, and it doesn't need to go back to the other ones because we have those links on the leaf pages. Just get here, and here is just a normal linked list. So just traverse the linked list until you get the last one. That's what the B-tree gonna do. It's pretty simple and highly effective for most of the data types, right? So what does operations we can do with B-tree? Most of the operations, the comparisons we can do with B-tree. We can do equalities, like find key equals X or whatever. We can do inequalities and range, right? Something that's larger to or smaller to or in between of them. That's a range comparison. We can do order by. So by default, when you create a B-tree, it's created in ascending order, sorry. It's created in ascending order, but we can change this on the index creation. We can change the order. And we can also use the like operator. But remember, we need to have a string, not the matching on the beginning, or else it won't be able to use that index, right? So those are the basically operations that can be done with B-tree. So those are the majority of operations we do daily, right? That's why it's so good, and it works with basically almost all types of data. So integer, varchars, and many different types. Anything that can be compared like this way would fit for a B-tree. So we also have the gin. It's not the alcoholic thing. But it's also good. So it's an inverted index. Anybody knows inverted index, how they work? Yeah, good one. Here, if we take a look here, we are indexing the key values, right? And then we have the content there. So in an inverted index, we index the content. And that's why they're so good for diagrams, for example, when we have a text search. So you get the content of all those texts. For example, let's say I have this text here, right? So I'm gonna get the word generalized and put on my index. And then for all the places that I find the generalized, the keys, they're gonna be just as part of this one. So we're gonna have in the index, instead of have that many entries for all the page addresses, we have only one entry that's generalized, and they're gonna hold all the addresses. This is easier to understand, right? So, for example, here we have the word whoever, the one that I can read from here, really need glasses. So we have the whoever. I can't tell. Many, myriad, something like that. So here is the word that we have, right? So it will link for the next leaf page. And if you see here, instead of having the IDs, we have the words, and then they hold the IDs. And the implementation here, we can have just a normal B-tree, or we can have a listed, linked list. The implementation down here, it varies from the implementation. On Postgres, they use a B-tree here as well. So, but yeah, this is how inverted index work. And this is why it's so efficient when we search on text, for example, compared to B-tree. Because I get all the words here, and I have all the places and positions that they hold. So I only need to find the word. It gets to the word, and there, okay, I just show everywhere it's in there. That's a problem that we have. We have expensive updates. So remember, well, every time that we change something here and we change the rule or whatever, we need to update the database, right? So because of that, we can have a lot of logs as well, because we need to log the index when we are updating the index, right? So I think I move it to. So the updates, they are very expensive. Postgres try to work around with a strategy, what they call fast update. So what they do is they defer the update for the index to a later moment. They create what they call pending list. We have a list of words that needs to be updated, so it's just a pending list, and eventually will be updated to the index. So when when we have a select, it searches both the pending list and the index page as well. But the problem is, when this pending list gets flushed, we're gonna have a lock. And depending on the size of the pending list, we have a configuration parameter that I do not remember now. But depending on the size of the pending list, that can take really long time. There was a problem on, not GitHub, the other one that competed for GitHub is the GitLab. There was a problem with GitLab, I think 2 years or 3 years ago. They had really high, long updates, concurrency, because they have really hot words, like, for example, update or Git or whatever. They have some hot words there. They were going a lot to the pending list, and the pending list they are taking for around like 15 or 30 minutes because they're pretty large. And every time they're flushing the pending list, all the updates or inserts, all the transactions that was on the gene, they will take around 3 to 4 minutes. So we don't want to wait. And in that case, they have timeouts. So a lot of timeouts on the application just because of the pending list. So this is a problem that we have with Gym, right? And depending on the application, the circumstances, it's better to make the pending list smaller. So we get them flushed faster. So we just distribute the load. Instead of having a huge flush, we flush among the time. Depending on the application, if we do not have the high intensive and thing, so we can make it larger actually, and probably gonna flush it at night or sometimes nobody's using, but still have the risk it gets hot during the middle of the day, right? So, but it highly depends on the application, and it's something that we need to understand and keep in mind that happens for the gym. Oh, the next one that I want to talk is the BRIN, the block range storage. This index is very misunderstood. And when well used, it can improve a lot of performance because it's really, really small. So it doesn't index the data, it indexes blocks. So on the index, everything that we have is what is the data that starts the block and the data that ends the blocks. So we need the data to be ordered. A very good example, time series database. So when we have a time series database, we always have an ordered data because, well, it's time. And time series database, they do not hold updates. That would be a problem, remember, because when you update on Postgres, it just changes the row and can put in another block. So in that case, for a time series database, what we're going to have something like this. We have one block, so that the data in this example starts in 1947 and ends in 1951. The index entry will have the blocks, in this case, page number 1, the starting point and the ending point, and that's it. If you do a select, everything that is in between here gonna be found by the index and gonna lead you to the block. Doesn't matter how many data points I have inside of this block. I'm gonna have only those entries in my index. So this index get like usually a few kilobytes of size for terabytes of tables. For this type of application, it's really highly effective. It doesn't work well on applications that we have updates or high number of updates because it will mess up with the order here. So it's just gonna be a pointless index, won't work. And this is the point where people do not get it. It's a really good index, but for very specific situations, right? Just like, for example, a hash index that I didn't put here. It's a very good one, but it's a very specific situation. You cannot do range operation on a hash index. You can only do a equality comparison on a hash index, right? So it is quite effective, but for those very specific cases. And the last one I want to talk today is the generalized inverted search tree. So it's an index that really fits well for dynamic data that work in blocks, especially for geographical data and polygonal data. So how does it work? It uses a B tree to create entries of interpolating blocks or interpolating data. So for example, if you have working with a data set that you have geolocation data and you want to see if those two locations, they are close to each other, that's the index that you're going to use. If you're working with biology and you want to have a really long DNA something, and then you have some comparisons in between the types of DNAs, that's the type of index you're going to use. They're highly efficient for those type of operations. But they also can get hot as the gene. They have the same problem, right? And they can get really large because depending on the data type that we store, we can store a lot of data. For example, if we have a polygon that have 5 faces, you need to store at least 5 points. If you have a polygon that has 100 faces, for every data point, you need 100 points. So it can get really, really large, but it's highly efficient. And for those type of data, they're a lot better and faster than the gene index. And a good example that used a lot is PostgreSQL. That's one of the main indexes used by PostgreSQL. Yeah, those are not the all index types that we have on Postgres. We have by default few others like the hash. We have GIS or OPS and other types. And we also have a lot of extensions that implement their own indexes. As I mentioned, we can implement our own indexes with types and different. So sometimes you have just a fancy type of data, fancy application that we work with, and we need our fancy indexes. That's possible. So we can implement in C, in Python, even in PSQL. That's the standard language for Postgres, and can be implemented with no problems. And this comes with a challenge. How can we find the right index type for our data? Sometimes it's tricky, right? So some hints. We should think of an index just like a specific data structure that supports a specific type of data with a limited type of comparison. First thing we need to understand is, okay, what type of data are we storing? Are we storing integers and normal data, like varchar and something? Well, it looks like to be a good thing for a B tree. What type of operator are we going to use? What type of comparison are we using? Oh no, we're using just equality. Well, if just equality, maybe a hash index. Works pretty well if equality is smaller than B3, right? Yeah, sounds good. Oh, no, we need to do a range comparison. Well, if we need to do a range comparison, a hash index does not work anymore. Now we go back to the B3. Oh, and we are implementing a text search. Mm-hmm. Yes. Yeah. Yeah. No, it doesn't need to be the same. Yeah, exactly. You can. That's a really good example. So you go for a website, buy your food, right? You search for a specific restaurant using a B3, and it's gonna use the GIST to build the route. Yes, exactly. You can. It doesn't need to be the very same index type in one query. Exactly. In one query. So those are things that matters, the operator type and the data type. Also, cardinality matters. As we talk, like if we have a lot of one column that is just true or false, that's really low cardinality, a B3 index would be useless. The database would never, ever use your B3 index if you put there. For the other hand, if you use a gene index, that will be likely to be used by the database. Because a gene index, it doesn't do a search, it does a bitmap operation to find the data. In that case, it's very likely to use the index because it's just gonna be pretty small, gonna be just very light operations using a bitmap one to find the one. So in this case here, if we have a really high cardinality, like a primary key, well, it's likely to be a B3 again. Whereas a tree is highly efficient to find those high cardinality values, right? So all those things we need to take you can take in consideration to start choosing the right index type for our application. So we can have multiple columns and partial indexes. I created just a few minutes ago an index using two columns, right? The ID and the name, so that's pretty normal, just like any other database. We can also have partial indexes. And this is interesting. Let's say we have a table user, for example, and on the table user, we have the zip code. But the zip code can be null. So if I have 50% of the zip codes as a null and I use a B3 index, it's likely not to be used. However, if I create the index telling them I don't want to use, let me see if I have the example here. I can use a where clause. Let's go back to my indexes. Did I drop them? Okay. Yeah, I do not have, so I create I hope I'm doing the right syntax. So I can tell the database, I want to create here, but only for the names that are not null. Yeah, it's creating my index. So in that case, the index will only have names that are not null. If I do a select where names is not null and name what of something, this index is going to be used. So it's a partial index. It will index only a portion of the data. It can be highly interesting and effective. So not all these indexes, they support those features. For example, BRIN and hash, they do not support partial indexes. And B3, it does multi-column index and also work pretty well with those things. So if we're gonna do a multi-column index, it's definitely going something to B3. We can use functions and expressions in our index definition. Remember that the lower example, we can just create an index like this one. So every time that the user do this select here, select stuff from users where lower name equals Charlie, that index is going to be used because it's using the function. We can create index with expressions as well. And it's funny how many times I've seen applications using, they're just concatenating and casting things inside of the select on the web. And when you get really annoyed for the developers, say, man, if the index is not working, okay, go create the index for him and be happy. But remember, with great powers came great responsibility, as user to say Uncle Ben, right? So one would be tempted to create multi-column index to benefit from an index scan, right? Or to create indexes, functions, and all. Every time that we do create an index, we have overhead on the database. What I said from the beginning of the topic, indexes are amazing for searching data, but they are horrible for updating data. It doesn't matter what type of index. Ones are worse than the others, but they always add some overhead on the database. Right? So one technique that we can use, for example, for index-only scans, because there are many techniques we can try to work around those overheads. Postgres provides this unique, not unique, the include keyword. We can create an index that does not really have on the index the column. We just tell the database, buddy, I want to create this index. See? I want a cover index on the login ID and the full name. But I don't care about full name. I don't want the full name to be on the index. I just want to have the data there. So when I do a select, I have a covered index with full name as well. We can use the include.
So that will have the full name in the base.
Yes, it will. Not in the keys. Exactly. And it won't mess up much with the database. For example, if we have a unique key, unique constraint on that index, still works pretty fine. If we have a unique constraint in login and ID, you don't want to put the full name on the index, right? Because they're going to mess up with the unique key. Oh yeah, you're going to update, but you're going to update the index anyway. With great powers come great responsibility, right? So yeah, nothing comes for free. No, it is. That's why I say here, still adding more data to the index means larger index value, which its own can be a problem, right? Nothing comes for free on the database. Yeah, it has to. Exactly. So, as I said, adding and dropping index on production can be a problem, right? Because we can hold an exclusive lock. So Postgres has a concurrently keyword that we can add an index concurrently. So it will not add lock. The database just keep working normally. It will create the index, it will try to create, but it can fail. One thing that you need to keep in mind, it can fail. Because if the table, someone or the application holds, for example, a lock on the table, an exclusive lock on the table for too long, that operation will time out and that index creation will fail. It will not affect the database in the sense that the database will not try to use that index. So you keep working fine, but we're going to be left with invalid index there. That we need to drop that index, invalid index, and try to create again, right? But usually, most of the times, it's worked fine. So if you go for production and you want to create an index or drop an index, that's the way to go to use it concurrently, right? No. But that's a good one. That's a good one. And so always make sure that that operation will succeed. So go back and see, yep, succeed, the index is there, it's not invalid. So, or else you have to retry and create the index again. And we came to the conclusion. So, as you saw, it's highly important to understand how Postgres organizes data, because it gives us the background on what we're doing, right? So creating an index and creating tables is just not plain creating things. It's not go there. So every index works in a different way. The same index with different operator classes, they work in a different way. So a lot of problems that we solve from the application side, they've already been solved inside of the database. We don't need to reinvent the wheel. So then understanding those fundamentals, the basic concepts, they're very important. And asking why? Why it is implemented this way? Can it be better? Because Postgres is a live community, right? So there's a lot of things to be improved, enhanced, fixed. So we don't need to fix them ourselves. We can just propose and people ideas, right? So there are many, many ways that we can contribute and collaborate with the community. Sequential scan is not always bad. It can be improved. Remember the example that I gave that we reduced the scan from 2 seconds to 85 milliseconds. It's more than 10 times, like 20 times optimization without any indexes. Just playing around on how the scan is done by the database. So it's not always bad. It can be a good thing. Sequential scan is the best method to traverse a table. If you need to traverse a table, that's the sequential scan on Postgres, because how the table is organized, right? And it can be done in parallel. So we can enable the parallel queries, but remember to be careful. You don't want to put 2 main loads on your box, right? If you have 128 machine, do not allow 10,000 connections on that machine, please. That won't do any good. Well, indexes are tools built to help improve performance. That's it. That's only purpose for index. And performance to what? Performance to search. So indexes are expensive to traverse because they have a lot of random I/O. They've been traversed as a B-tree. It's not just like traversing a plain data table. It's a B-tree, so it requires a lot of I/O from one page to another page because they are not physically close together. There are many, many ways to go wrong with indexes, like picking the wrong index, using a B-tree to index a JSON. Back in China, I was hired as a consultant for a company. They were moving their application from Oracle to Postgres. And the Postgres was really, really slow for everything, especially for inserts. It was painfully slow. And they were about to give up and go back to Oracle. And I think, let's try to understand. So I talked to the application team to understand the architecture of the application and the language, how they're doing things. I didn't see any problem from the application side. Okay, let's take a look on the database. So they didn't only change the database. They changed it from the Oracle to Postgres, but they also changed the data structure. On Postgres, they wanted to use JSON, which was not a problem per se. The problem is the main table that they had 7 columns and 117 indexes. They were using B3 to index the JSON, the columns inside of the JSON, you know? They were using those bits. And I thought, man, you know, this is not how it works. Let's do an exercise. On the weekend, we're going to do exercise. We dropped that index, and we created a proper gene with the proper operator for them. And after the cache has been built, like one week and a half, the performance was outperforming the Oracle from the application side. Foreign keys, the constraints, all of them, not on foreign keys, they do not create index by default on Postgres. When you create a foreign key, you will also need to manually create the index if you want the index on that one. And usually it's a good idea to have the index on the which table? Do you create on both tables? In one of the tables? That depends. The answer is depends. Well, what happens if you do a lot of updates on your parent table? It has to check the child to see if it's not violating them. In that circumstance, would be a good idea to have an index there as well. So if you have, well, if you can do an inversed search, right? You can also search on the child table to find the parent. In that case, it would be a good idea to have on the parent. So it highly depends how your application works. You have to be unique. Yeah. And then, yeah, the question is, do you always need index on the fork? It highly depends. Right? So, and then depends on how the application is going to work. And that's how it's important to understand how those things they work, right? The fundamentals. So not all the indexes are the same. So as we saw, different indexes, they have different behaviors. They have even different internal data structures. They do not work as the same way. They have different comparisons. It's important to understand which one work better, which data type. That's just the example of the JSON. Please do not put a B3 on JSON. You can use a gene, right? So different indexes work with different data, cardinality, and distribution. That's the same thing, I just mentioned that. So if you have data that has really low cardinality, it's pointless to put a B3 index there. The database will never use that index. Doesn't matter how you force the database. You can strangle him if you still won't use that index there, because the cardinality is too low. If you put a better index, for example, a gene in some circumstances, yeah, that's very likely that the database would use that index. Indexes are expensive to maintain and update data. Some indexes are more expensive than others, but they are all expensive. In a way or another, they are expensive to be maintained. And index should be used with caution. So always, when designing any application and database, always design them without pre-optimization. Do not try to optimize in advance. Do not create any index, just the good old primary keys, the unique keys that you need, that's all. When the database starts growing and you see the data pattern, how the application works with your data, now you have information to start building indexes. Doing pre-optimization usually is a bad idea, because for the more we test, we never know how it's going to work on live. Sometimes we believe, oh, this column going to be really, really used, and then nobody cares, and the application changes and the pattern changes, and we still are left there with an index troubling the updates and the inserts, right? So, and that's it. Thank you, guys. I hope you learned something. I should have one for questions here. I think I forgot. Questions? Yes, I'm going to put right on the GitHub as well, where I have the data set that will be there. Welcome. Thanks, everybody. If no more questions, you are free to go.